To welcome Johan Gilchrist to the department to give the BSL seminar. He got his bachelor's degree and PhD at the University of British Columbia, and he's currently working as a glaciologist with Bruce Jack Gold Mine in northern British Columbia. You might wonder, what is the relationship between glaciology and gold mining? And that's the subject of an interesting discussion. He also spent 6 months working at the University of Oregon. He studies explosive volcanism. He's done some beautiful and elegant lab experiments. You'll see some of those today, I suspect. He's interpreted field deposits. He's also used Doppler radar to try and understand fluid dynamics as well. And part of the goal, of course, is to understand the mechanics of explosive volcanic eruptions. But this is also information and insights that feed into understanding the climate and facts of eruptions, and to improve our ability to forecast eruptions and then do something about it. So thanks so much for coming. And for those on Zoom, Roland's monitoring the chat if you'd like to make some comments or ask questions.
All right, thanks, Michael. And thanks to all of you for having me here. You may know me from visiting the department since Manara has arrived. If it was a secret, it's not anymore. And that's the only reason I've been, no, I'm just I like to think I do some elegant experiments. So I should share my screen here, I believe.
Looks good.
Looks good. Alrighty. So today I'm going to talk about the collapse dynamics of the largest explosive eruptions on Earth. I will be referring to these as catastrophic caldera-forming eruptions. Really, this should say some of the largest explosive eruptions on Earth. I won't be talking necessarily about Toba, which was the largest that I'm aware of 72,000 years ago. But we're going to be talking about catastrophic caldera eruptions such as the Hunga-Tunga one that just recently occurred, as well as Santorini, Sumizu, and Macaulay. The latter two being on the similar arc, Kermadec arc and the Uzubonin arc in the Pacific, and then Santorini being in Greece. This is work I've done with my former PhD supervisor, Dr. Mark Jelinek, and Emily Hoof, Dr. Emily Hoof at University of Oregon, who did a lot of the imaging of the Santorini deposit underwater around the island of Santorini, and then Sean Wankett, who's a good colleague and a master's student with Mark's group right now. And I'll walk through some of my previous PhD results from UBC, and then work I've done since that stems from the PhD work but builds on it through remote work with Joe at University of Oregon. That's Dr. Joe Dufay. Okay, so basically my methodology thus far in my short career has been to look at observations of eruptions when they occur, imagery we have of previous ones, as well as analyze deposits that they leave behind, and to use these observations in real time after the eruption and from field studies of their deposits. This is a digital elevation model looking down at the caldera of Sumizu, and you can see these beautiful terraces extending outward from it. And then this is the eruption column here of the Hunga-Tunga eruption that occurred the day before that massive one sent all of that erupted mixture to the mesosphere of all places. I'll take these and I will use them to design some scaled down experiments that occur in a water tank at our lab at UBC. And then we'll try to see if we can reproduce the main features of these eruption columns and their spreading clouds and the collapsing flows that spread out as higher types of density currents. And we know the source conditions. We can measure a lot of the features as they unfold in the experiments better than we can, say, in a real eruption. And then we can also look at the deposits they leave behind in the tank. So that's a top-down view of one of the deposits we've produced in the tank. And we can try to make links between the dynamics as they unfold that we see with key deposit features, and maybe be able to use certain features we see to then infer how some of the more ancient eruptions that we've never recorded before with modern technology behaved when they erupted. And it's important to do this because they've had major effects on climate and life on Earth in general. So then also I try to use these to develop some better conceptual models of these eruptions, and then can repeat this cycle and refine these models and observations. So that's basically how I approach volcanology, and a lot of my colleagues at UBC do as well. So a little outline for today. We're going to start talking about eruption column models, some popular models that I've used to guide the beginnings of my work and the hazards associated with them. Then we'll move on to these terraced eruption deposits that are one of the main subjects of the talk. And then I'll go on to sedimentation waves as the mechanism by which these eruption columns can collapse all their erupted material back down to Earth to form PDCs, and then suggest that these could be responsible for making these terraced deposits. I'll briefly show you some new eruption column models, but not go into them because they're very detailed. And then we'll move on to looking at catastrophic caldera eruptions that occur at these shallow water layers, similar to Hunga Tunga, which just occurred. And then I'll end by looking at a new conceptual model that we put together for the formation of these terraced deposits. But Michael has informed me that these terraced deposits might just be landslides, and everything I've done is useless. There is that possibility that Michael will tell me about maybe in a couple of years.
I said they were elegant experiments.
You did. I know. Thank you. Oh, we're keen to figure it out, though. Okay, so when you have one of these eruptions, you have a mixture of hot ash, pumice. So this is micron size to millimeter size ash. Pumice that can be centimeter to decimeter size, all the way up to meter size blocks, distributed turbulently in a turbulent gas solid mixture that is injected into the atmosphere at a very high vertical speed, which gives it a lot of momentum. It's more dense in terms of its bulk density than the surrounding atmosphere. So it would like to collapse, but it has all this initial momentum, so it rises. It mixes with the ambient atmosphere, heats that up, it can lose particles. All these processes go to drive its density to be less dense than the surrounding atmosphere, and it can then go through a buoyancy reversal. And that happens, so this is this momentum-driven fountain region, I'm going to call it, where it's being driven upwards by its initial momentum. It goes through a buoyancy reversal above that height. It will then transition to being buoyancy-driven with its rise rather than momentum-driven. It'll then continue to rise and spread at some level of neutral buoyancy. When it gets there, it will overshoot and undershoot a bit as it spreads out. So this has been a very popular model for explosive eruption columns for much of the history of our understanding of these eruptions, particularly in Dr. Steve Sells' time. And then it was also discovered, I guess, let's say 60s and 70s, that there can, and probably before that, that it can be significant collapses of these eruption columns. So if you don't go through sufficient entrainment of ambient atmosphere, before you lose your initial momentum as an erupted mixture or volcanic jet, then you'll actually collapse back down to Earth as a fountain. And this can, the physics of this can be very similar to a water fountain that you would see out on campus, for example. So these are the two end-member regimes of these eruption columns when they occur. And when I entered into the field of volcanology around 2012, it was quite popular that this was the two fates of these eruption columns when they occur. Now, if we know certain parameters, which I'm calling the eruption source parameters, so the radius of the vent here on the top of the volcano, the speed at which everything's coming out, its initial temperature, the volume fraction of the mixture taken up by the particles, as well as the distribution of sizes. If we know these 5 parameters, we can actually do a really good job of modeling these eruptions, say with computer simulations, to predict what regime they're going to be in and where all this stuff is going to go, which is how we predict the hazards. And a lot of work in the past has used these parameters to try to define which suite of these parameters together define a boundary between these two column regimes. And the typical hazards associated with these, falling ash and blocks out of the eruption column. Right here, you can see all the falling ash out of the 2015 eruption of Calbuco. You can also, these ash clouds, even if you can't see them as a pilot in an airplane, they can still be a high enough concentration to take down your airplane, destroy the engine. So they're very hazardous. And then, of course, there can be SO2 delivery to the stratosphere. So if these umbrella clouds spread in the stratosphere, you can distribute reflective sulfate aerosols there and reflect sunlight for years after and cool the Earth's surface by 0.5 degree, maybe even more, depending on how much sulfur you deliver there. So you can have some pretty drastic and abrupt climate effects. If you go through column collapse, you have deadly pyroclastic density currents that can spread. They usually spread kilometers to tens of kilometers away from the volcano, but in some cases can go hundreds of kilometers. Above these, and they destroy everything in their path. They're responsible for thousands of deaths of humans over human history, probably more than that. When they enter the water, they can generate tsunamis as well. And then also they generate their own ash clouds that rise above them and can spread at some height, sometimes lower than the main umbrella cloud, sometimes at the same height. And they can go up to the stratosphere, which was the case for the eruption of Pinatubo in 1991. Okay, so if I just go back, these hazards are pretty different from each other. There are some similarities in the Phoenix clouds and the buoyant plumes, but the pyroclastic density currents for forecasting hazards, we really want to know when those are going to occur and how far they're going to go from the volcano. Now, a lot of my PhD work was to look at a growing body of evidence for eruptions to actually occur in this intermediate regime, where you get a hybrid behavior. You get both umbrella clouds spreading in the atmosphere and PDCs and collapses ongoing at the same time. And in fact, it seems most of the eruptions in the 20th century, the largest ones, have occurred in this regime, as well as the 19th century. And this has been compiled by Edward Kaminsky and Claude Gelpart in their 2001 paper. And a lot of my PhD work was to actually expand the source parameter range for this intermediate regime. And it's been thought that this was actually an exception to the norm, that the norm was really the buoyant plume regime and then sometimes a total collapse regime. But I think there's enough evidence now that we're starting to realize this partial collapse regime may actually be the norm, not the exception. Okay, so looking at the sizes of these eruptions and talking about these catastrophic caldera-forming eruptions, the images I just showed you, those are from stratovolcanoes. You have a cylindrical vent and a magma chamber below feeding it. Catastrophic caldera-forming eruptions can actually have such a large magma chamber below, they can create what we call a caldera, where the central roof can collapse as ring fissure eruptions open around, and that can go down, and there's some complex dynamics that can drive those eruptions. But the point here is that they're very large, much larger than the images I just showed you. Dr. Self and Chris Newhall produced one of the first scales for measuring the size of these eruptions, or all eruptions in general. That's the volcanic explosivity index, basically a log scale of the volume that was erupted. If you look at Mount Tambora's eruption and Mount Pinatubo's eruption here, you'll see the area around those volcanoes that was covered with at least 1 centimeters thick layer of ash. And then if you look at Mount Toba, so those were 2 cubic kilometers of erupted volume, dense rock equivalent, that is, 25 cubic kilometers for Tambora. And then if we go up to Toba, which was 74,000 years ago, much larger area that was covered in ash and 2 orders of magnitude more material that was erupted. So a much bigger eruption, cataclysmic eruption for Southeast Asia, and potentially affected the climate significantly. So understanding those eruptions is important. However, it seems from the volcanic rock record that Toba would only occur every, million years. So hopefully not in our lifetime. Now, previous work I've done with Mark and David Jessup and Olivier Roche was to do some experiments and combine field evidence from studying the deposits of these larger eruptions and demonstrate that they have a tendency to occur in collapsing regimes. Part of this has to do with the fact that their vent areas can become larger during the eruptions and are typically larger than stratovolcanic eruptions. And you can think of this as, say, if you have the same mass flux coming out for a relatively small cylindrical conduit, and then you have an annular conduit with a larger area, it's like taking your thumb off the hose for the same flow rate. The fountain coming out of the hose is not going to go as high. It's less likely to go through buoyancy reversal and rise and spread. So it's more likely to collapse. And we see evidence for this in pyroclasts as well that show a decrease in gas content in the erupted solid products when you go from the initial stages to the latter stages of the eruptions. Okay, so terraced deposits. if Michael were to give this talk, he would refer to these features that I'm calling terraces as sediment waves. I think that's more the norm term to use. I'm going to call them terrace deposits though for this talk. And what I mean by that is that you have a caldera rim that's underwater here in Sumizu on the Uzubonin arc. And as you go down the flanks of this underwater volcano, you have step-like changes in the bathymetry rather than a smooth change in the bathymetry. So it's kind of like terracing going out. Now they're axisymmetric around the caldera. So, okay, you can see the fronts of these are paralleling the caldera rim as you go out. They're approximately regularly spaced. And the slopes, the uphill slope is relatively shallow. That's what I'm calling the back-facing slope. And then the forward-facing slope is much steeper, almost like a cliff. So I'm just going on, you can see a profile here of these just to illustrate that. I just want to make a list of these observations because we're going to use them to compare to our experimental deposits and see if we can reproduce some of these key features. If you look at a seismic profile going through another one of these deposits, this is Macaulay Caldera. This is just north of New Zealand. You can see that there's also apparently a decreasing wavelength, so crest to crest distance between these humps or terraces as you go from the near field close to the caldera rim to the far field. So as you move away from the caldera, the wavelength appears to be decreasing. And then the question I'm asking is, are these terraces indicative of a certain eruption column regime and therefore mass transport mechanism, so that such that if you see terracing, does that immediately tell you a lot about what the eruption column was doing when it placed these terraces? Now, it could also be that these were landslides and slumping features. So let's say you place a bunch of tephra, so volcanic material after an eruption, and it's smooth, and then you shake it and you can get some progressive destabilization, form these terraces as well. That's what's been suggested. But I'm suggesting that it could actually have been formed by the collapse of these eruption columns. Okay, so now we're going to move on to what this collapse could look like and how that could produce these terrace deposits. And to do this, we're going to go to the laboratory. This is a deep, dark dungeon lab at UBC with no lights. And when I come out on a summer day from there, I have to go like this and recalibrate and then go out with my sunglasses. And I've spent long hours in there. But it's fun. And what we do is we have a meter-cube water tank. We fill it with a dense salt layer at the base that continuously decreases in density to fresh water at the top. And what we're doing is we're trying to mimic the density profile of the atmosphere in the troposphere on Earth. So that's our environmental stratification, as we call it. Then we're going to inject a relatively dense mixture of silica sand that is modeling these centimeter to decimeter sized pummices that occur in these eruptions and these volcanic jets. So we mix that in vigorously in a bucket up here with water, and we inject that as a multi-phase jet into our tank to see if it rises buoyantly and spreads or collapses or does something in between. Now, we do add some finer particles to this in other experiments, and I'll show you what those look like. But for the most part, we're just sticking with the silica sand because we want to see what the inner dynamics are. If we include the fine particles in every experiment, we actually won't see what's going on in the center where all the action is. We keep the source parameters I mentioned earlier constant throughout the entire experiment. And for these large eruptions, for most of their eruptive phases, this is a good approximation. But in the future, we want to be able to vary these to see how those effects would play out in the dynamics. And then finally, we're doing this in water. So this is, in the case of a natural volcanic eruption, it's a turbulent multi-phase flow. We have turbulent air particles mixed, I'm not going to say homogeneously, but approximately homogeneously in that mixture going up at height. There are thermal effects in that, the heating of the ingested air to drive a buoyancy reversal. We can't capture that directly because we're using an incompressible fluid here in the lab. So we can't capture that thermal expansion with height in the column in the lab. But what we can do is we can tune the buoyancy of the interstitial fluid that we put in that source mixture. We can actually make that fluid buoyant, or we can make it dense relative to the bottom layer here. So by doing that, we're saying we're going to take the cumulative effects of thermal heating of ingested air and just put it all in at the source, so we can capture that in part. But I'm more, in these experiments, we're more concerned with the mechanical mixing effects and how that can drive spreading at height or collapse down to the tank floor. So when we run these experiments, we see, at least qualitatively, we're able to capture the main features of our three regimes of eruptions, particularly the umbrella cloud spreading and no collapsing flows for the buoyant plume regime. Then in the total collapse regime, no umbrella cloud spreading, everything collapses to the tank floor, spreads as a ground hugging gravity current. And then the partial collapse regime, we actually see both behaviors simultaneously. The nice thing about this partial collapse regime experiments is that what we've shown here is that even with steady source conditions, source parameters, you can still get unsteady processes operating in the column and unsteady fluxes of material collapsing to the ground and spreading into the clouds. Okay, so that's important because in the past, it was interpreted that you'd see some of these deposits that showed hybrid behavior from the two end member regimes occurring potentially at the same time or in quick succession. And some folks assume that the source parameters are switching between these end member regimes during the eruption. But here we're demonstrating that doesn't have to be the case. You don't have to invoke that explanation. So that's a pretty important result here. It relaxes the time-dependent constraints on the source parameters, essentially. So
you keep the radius and the velocity controlled?
In the tank experiments, yeah.
All the time?
Yeah, we keep the velocity coming out constant and the radius constant as well.
So what do you change?
Between experiments, we can change the velocity, the particle volume fraction. Sorry, I meant during a single experiment, we keep those constant, but we vary those source parameters from one experiment to the next.
And the source parameters determine if this is buoyant or collapse?
Essentially, yes. So I'm about to introduce those source parameters we use to characterize that, and I'll map out where these experiments plot on that regime space. So yeah, let's do that. These source parameters are going to be the particle load. So this is the particle volume fraction of the mixture that I went through earlier. It's just the volume of the particles divided by the total volume of the mixture. And then the source Richardson number. So this is a balance of the driving momentum that is driving the mixture upward into the tank. And that is the denominator. In the numerator, we have the buoyancy force that's acting to pull the mixture down as it enters the tank. This also has implications for the efficiency of mixing as well. I'm not going to get into that, but basically using this as a source condition has been proven to be a good way to predict what regime we're going to end up in with our multi-phase jet column. So the nice thing about using these, and this is the essence of scaled experiments, is that we can define these for natural eruptions as well. And that's what allows us to scale these turbulent multi-phase flows from nature down into a tank lab to investigate these critical mixing processes that determine the strength, the regime of these eruption columns in nature, as well as our multi-phase jets in experiments.
What do you mean by volume of particles?
So we have, when we mix the particles into our delivery bucket, we have a certain volume that goes in there, and that's going into a certain volume of water. So we just take the volume fraction of that mixture that's occupied by the particles. And we can define that for eruptions as well.
So as a starting condition, that's well defined, but then that will vary throughout the plume. Yeah. Okay.
Yeah, you mix in ambient water, you're diluting.
Yeah. Okay.
You can also get local. It's complicated. We'll get there.
What do you mean particles? I mean,
these are the stand
silica.
The silica stand particles, they're about 225 microns in most of these experiments. And we also have silica powder we use that's 75 microns as well. One is simulating sort of centimeter-sized pumice, the other simulating micron-sized ash.
And they touch each other?
No, they shouldn't in this water solution.
Spread out.
Yeah, it's borders on dense and dilute flows. That can change depending which flow in the experiment you're looking at. But in the cloud, in the rising cloud, the buoyant plume regime, it should be fairly dilute, especially up in the cloud due to the entrainment of ambient fluid. When you get these collapsing flows and the dense currents that flow along tank floor, you could potentially get interactions between particles, what we call four-way coupling.
And all the particles have the same, identical?
Yes, we sieve them to make sure it's a very skinny Gaussian around 225 microns.
Okay. So the particle collisions, is that because the water has higher viscosity? What's the reason?
That you wouldn't have them as opposed to air, you're saying?
Yeah.
That's my understanding. I've talked to Olivier Roche, and he's not aware of any studies that actually showed particle collisions in water in these water tank experiments. In air, we think it happens in volcanoes because you can get ash aggregation. So if you have wet ash particles, they can tend to stick to each other.
Collision is, you're making the argument that the collision is prevented by the water. So I'm guessing that's because you have to squeeze the water out of the way.
That's
in these experiments, your lubrication forces will keep most contact from happening.
Yeah.
Yoshi, you've said turbulent several times. Can you remind us of your Reynolds numbers?
the Reynolds numbers for these are as high as I believe 5,000 to 6,000, and I'm trying to think of the minimum Reynolds number for our lowest fountains in this suite of experiments. I think is around 3,500.
Which is probably low compared to the natural environment.
It is.
Yeah.
Yes, it is. Yeah.
Let's make sure Yoshi has time to get through it.
No, that's fine. Okay, so when we plot, where are we at? Okay. When we plot the source Richardson number here on the y-axis, this is in log space, and as you go up on this axis, the jet strength is decreasing. So basically what's happening here is the source velocity, you can think of it, is decreasing as you go up here. They don't rise as high into the tank. As you go right here on the x-axis, this is particle volume fraction increasing linearly to the right. And then in pink, we have our experiments that occurred in the buoyant plume regime. Then we have partial collapse experiments here in green and total collapse experiments here in blue. And one of the key observations we found is that we vary these source parameters between each experiment. We see a continuous change in the height at which this top intruding cloud occurs, the emergence of lower clouds as you move closer into the partial collapse regime, and then the disappearance of the umbrella cloud and some of these lower clouds in full collapse as you go into the total collapse regime. So this implies that as you vary these source parameters of these multi-phase jets, they're continuously transitioning through these regimes rather than passing some critical thresholds that change the behavior abruptly. Now, this would have implications as your source parameters change throughout an eruption, right? That's why I bring that up. Okay, so just to compare with nature, we do have good constraints on the eruption source parameters for Mount St. Helens in 1980. And this would be plotted here within uncertainty. And on this regime space, compared to these regime boundaries that we've defined with our experiments, it would occur in the partial collapse or total collapse regime. And that's indeed how it appeared to behave when we observed it and based on the deposit observations thereafter.
I'm sorry, but how is that determined from Mount St. Helens? I can see how one can estimate the particle volume fraction, but the Richardson number, was that because of the phenomenology of the plumes observed?
Yes.
Yeah, okay.
That's primarily where I got that from
Okay.
Dr. Van Andrews'
That's
work.
great, yeah.
Yeah.
Thank you.
Yeah, there's
Yeah, that's okay. I just
spent a lot of time on that. I've tried to capture uncertainty though with the size of this box. But measuring eruption source parameters
Very
is
hard.
notoriously difficult. I should just generally make that clear to everybody. So anything we can do to try to constrain it better is going to be helpful moving forward. Okay. So one of the main things we observed in these experiments is that the collapses in the partial collapse and total collapse regimes off the top of our volcanic jets or at some height and along their columns was not continuous. It actually occurred in these packages and it appeared to be periodic. And so what I've done is taken a total collapse regime fountain video here and I've differenced the frame. So subtract the previous frame from the current frame. And what that does is it highlights the wave fronts of what I'm calling these sedimentation waves falling out, not to be confused with the sediment waves that Michael refers to my terraces as. So sorry, some confusing jargon there. But these are sedimentation waves, a dynamic process. Terraces are what the features are in the deposit. So when we look at the top of these fountains in this, oh, it's not showing up there. Oh, it has to wait for the video to finish. And there we are. And it's going to do that. Okay, just bear with me. Okay, there we go. So we can look at the top of these fountains oscillating up and down with time. And And when we look at a time series of that, we see that before every dip, local dip in the height of the oscillation of the top of these fountains, there's a large sediment wave that descends around it. And then it recovers and then repeats this process. When we look at the deposit, we see 4 distinct axisymmetric terraces. And we think that that might be related to these 4 main sedimentation waves we've seen. Some of the smaller terraces that may be faint and appear there could be related to these smaller oscillations in that time series. But this is suggestive that there could be a link between the sedimentation waves, the oscillations of the fountain, as well as the terraces in the deposit. Now here, what we're going to do is show you the experiment where we've added the fine particles now, because we were interested to see, okay, if you have a more realistic particle size distribution that approximates the natural eruptive case better, do you still get this terraces forming in deposit? We also want to see if there's sedimentation waves, and we think we can because you can see the radius and the height oscillate at approximately the same period as we saw in the previous experiment that didn't have the fine particles, but you can't track the sedimentation waves as they go down all the way to the base and then spread as ground-hugging density currents. But what you can see is what I call phoenix clouds rising off those ground-hugging flows intermittently here. Sometimes you can see those flows poking out here. Importantly, after we let those fine particles settle after 2 days approximately, we notice that there's still terraces in the deposit, and those fine particles appeared to blanket an underlying terrace deposit that we think was primarily formed by the sedimentation waves depositing the coarse particles as terraces.
In terms of the sediment waves, are they coming down roughly at the same radial distance from the axis? Or are they actually coming down at different radial locations?
That's a great question. So I measured that. There is variation, but at the order of magnitude that their length scale should be from the axis should be set by the top, the average radius of the top of the fountain. And there's some work by Stuart Turner, as well as Ross Kerr, I believe, and Lynn Bloomfield to do those geometric relations between the fountain top radius and the radius of the collapsing flow. So the largest eddy size at the top of the fountain should set the maximum radius of the sedimentation waves.
But then your deposits are different distances from the radial axis, though.
Yes, they are. Yeah. In these experiments, I did the measurement, and they all occur within I found what the largest sedimentation wave was, and all the prominent terraces appeared within that radius, what I'm calling the sedimentation wave impact zone radius. But we will return to that later, but that's a very good observation. Okay, I'm going to skip that because I've explained that. Okay, let's go back to the terrace deposits in nature. So more work we've done. We've looked at a terrace deposit produced by one of our experiments, and we tried measuring wavelengths as you move outward from the source. And we did notice with manual measurements, as well as doing a Fourier transform of the profiles of them, that the wavelength does appear to decrease with distance from the source, just like we see in nature. They also appear to be axisymmetric around the caldera. They do appear to be regularly spaced, although that spacing is decreasing as you move out. And then they also, in some experiments, show this backward facing slope towards the source being shallow slope versus steeper on the outward facing side. Okay, so to answer one of our initial questions, are these terraces linked to a specific multi-phase jet column regime? In our experiments, that appears to be true. Okay? In nature, I don't think there's been enough work done yet to prove this. So if we go back to our regime diagram, if you see deposit terracing, we see it in the partial collapse regime, although it can be very faint, and then it's very prominent in the total collapse regime. So it suggests that as soon as you see deposit terracing, you could be somewhere in this source parameter space. So it's a way to go from a qualitative observation to some quantitative constraints. And then in the buoyant plume regime, we don't see any terracing. We just see a monotonically decreasing deposit thickness with distance. Now we're going to go to these catastrophic caldera forming eruptions. And these are going to occupy this parameter space here, the ones I'm going to focus on. And Well, I attempted in my big PhD paper to really heavily revise some conceptual models for the partial collapse and total collapse regime and try to capture these sedimentation waves effects. There's a lot of knock-on effects from these as well. And a lot of that would be veiled by the fine ash layer around these eruption columns in a real eruption. So you wouldn't necessarily see what's going on in the middle. I'm not going to walk through these in detail right now, but they are in my published paper, and I'm happy to talk you through it later. But that's the goal, right? We're trying to revise these conceptual models to be more informative and include more detail. So now we're going to look at what happens if we have a shallow water layer in our tank. And this is to try to model these same dynamics, but for an eruption column that's rising through a relatively shallow ocean water layer, for example. So very similar to what happened with the Hunga-Tunga eruption. And part of the motivation for this is that we found these naturally terraced deposits around calderas that are in these shallow marine environments. So this is Santorini in Greece. This is from Paraskevi Numiku and Emily Hoof's cruise there, where they were able to image the bathymetry surrounding the island of Santorini, and you can see the striking terracing going out from the caldera rim there. We also see it at Sumizu on the Izubonin arc, and we see it at Macaulay caldera. Although it's not always fully axisymmetric around the caldera, sometimes it's limited to one sector around it. But the main question we're going to ask, okay, let's look at those dynamics that we just saw in our experiments. And if we now do it in a shallow water layer, how is that going to affect the behavior of the sedimentation waves and the morphology of the deposits that are produced? And part of this is really what we're doing is we're introducing a very abrupt density interface here, right? Whereas we had a steadily decreasing density stratification in the tank, here we have constant density freshwater overlaid by an air water layer. So 3 order of magnitude drop in density in the ambient as you cross this interface. All the other source parameters are the same as the previous experiments. The main thing we're varying now is the water layer depth. Okay, so what does one of these look like, these experiments? Here we have a front view, and this is what I call a breaching fountain experiment, where the fountain, or the jet mixture rises through here into the ambient air layer and then collapses as a subaerial fountain back into the water layer. This is a top view synchronized in time. And the nice thing about the top view is you can actually see those sedimentation wave packages grow at the top and collapse around the central jet or fountain and into the water layer. You can also see waves being generated. And what we've been able to measure is that actually, come on, we can do this again. So let's watch it again. Here, well, I'll talk about the deposit. The deposit actually, overall, the terraces that first occur as you move out from the source occur at a distance that's larger than the innermost terraces in our previous experiments. Part of this could be because we're building up a thick deposit here as a sort of central plateau and burying previous terraces, and or we're creating new ones by flows going down this new central deposit here as well. But we do see terraces basically with overall diameters that are larger than what we saw in the experiments that I call the deep water experiments that I previously showed. Okay, and then what we think this could be linked to in part is that when you have the sedimentation waves descending around these fountains, the subaerial part of the fountain, and then it impacts the water surface, you're going to get some lateral spreading as it decelerates when it impacts that surface. And we think we can see that. We can measure the sedimentation waves as they fall here. And then if we assume that where we see this wave being spun off right here, measure that, we see potentially almost up to an increase in the sedimentation wave radius upon impact of about 2 times. Okay. So similar to our deep water experiments, we can map these experiments, which I call the shallow water experiments, on a Richardson number particle volume fraction regime diagram. And one of the main things we see in these experiments is that as we decrease the strength of these fountains, these shallow water fountains, the expression of terracing is constricted to a tighter radius, a shorter radius around the source. And as we go to really low fountains, we almost don't see any terracing and maybe potentially disappears. This could be because when you have very low fountains, the collapse frequency could almost be considered continuous and you don't have periodic descent. Yeah.
And in all cases, they have that inward sloping, shallow inward sloping feature.
I can't say that for all cases because I have not made digital elevation models of them to measure that directly. So here I have just measurements of where the outermost terrace visually occurs, and then just the qualitative observation that it becomes more faint. That's all I can say about that. The other thing is, as we decrease the water depth, we go from having terraces extending out, decreasing in wavelength, to the central plateau being formed as the water layer depth starts to become the same as the sedimentation wave penetration depth, which I'm not going to go into now, but basically that means once the water depth gets shallow enough, the sedimentation waves impact with enough momentum as a jet that they can actually scour the deposit where they reach the deposit rather than be depositional when they get there. And then when it's really shallow, you can see they can scour out to many vent radii out from the vent there. So the other thing I'm showing here is that we're trying to map realistic eruption source parameters for these catastrophic caldera forming eruptions onto this regime diagram. This is not a trivial task. You have to make a lot of assumptions about what are realistic ranges of those eruption source parameters that I went through earlier. We've attempted to do it just to see where certain mass fluxes coming out of these large caldera eruptions would map onto this Richardson number particle volume fraction space. And these numbers do match some of the estimates from deposit characteristics such as volume and whatnot from Santorini as well as Macaulay. Okay. So a potential model for the formation of terraces, at least for our experiments in these shallow water experiments, you have a fountain that gets established, you build these sedimentation wave volumes on the top, it descends, impacts the water, spreads a bit, generates waves. It then reaches the tank floor where it'll spread again. And now it's going to be spreading as a ground hugging gravity current. It can accelerate out as it first impacts and spreads, but then it will begin to decrease as it entrains and deposits material and experiences friction with the ground. This is what we can call a hydraulic jump. And so you'll see that the thickness will abruptly increase, and we actually see this qualitatively in top views of our experiments. You'll deposit a lot of particles when this occurs. And so the first one will go through that hydraulic jump, deposit the majority of its coarse particles, and then continue to flow. But then when subsequent sedimentation waves come, they will again be erosive, scour, then go through a hydraulic jump as they hit the first sedimentation wave. But they can accelerate down the steeper side of it as they flow past, scour a bit, and then go through another hydraulic jump, deposit, and then you, through this process, can progressively build more and more terraces. But you can also modify them. You can also, at much later times, begin to bury them, especially if you make a cone that could be at the angle of repose of the particles. So it's not just as simple as that, but we're trying to capture the initial stages of this process. Okay, so I'm going to go over some conclusions here so we can open it up for questions. I think one of the most important things for my PhD was that most well-studied large eruptions, explosive eruptions, appear to occur in a particle collapse regime. And there's a lot of support for this, not just from these experiments, but also from studying the deposits of some of the largest eruptions that we know of. So the partial collapse regime is actually really important to study. It's not just this ugly duckling that is annoying. It is actually maybe the norm between the two more popular end member regimes. The other thing is that even with steady eruption source conditions, you can have unsteady processes occurring in the column that drive periodic sedimentation events. And you need to understand that when you interpret the deposit. Then we've also put forward, let's see here, sorry. Yes, this model for how you can build terraces out progressively from the source through the subsequent descent and spreading of these sedimentation waves. And then we've also found that the water depth can control the morphology of these terrace deposits as well, where you can get a lot of scouring for very shallow water layers, and then very faint expressions of terracing on the outside of this, which is much different than the deep water situation here. So ultimately, what we're trying to do is take these qualitative observations, potentially quantitative measurements of the terracing, and use that to try to infer eruption source parameters, or at least begin to constrain them. And that's really important for some of these ancient eruptions where we have very little data about them, to just start making some traction in understanding what realistic source conditions can be for them. Some remaining questions. Do these terrace deposits occur on land? We don't know. Maybe they're very well, exceptionally well preserved in these shallow marine environments because you don't have rain, you don't have erosive events that can erase them fairly quickly in geologic time. So I'm not going to rule out that just because I haven't found one on land yet, that could be because it just gets eroded too quickly. There's been a lot of work by Michael and Kristen Foria on how pummices can change density during rise in submarine eruption plumes. There's a lot of complex physics in submarine eruption plumes that we don't capture in these experiments. Vaporization of entrained water before rise into the subaerial layer. How would these affect these dynamics? Would they change it? Would they preclude these dynamics from occurring at all? And then also you can have the formation of a pumice raft on the surface. How would that affect the impact of sedimentation waves with the water surface? Could that cause mass partitioning of the sedimentation wave, where some of it flows along that pumice raft on the surface, while some of it goes down underneath? Does it entrain some of those floating pumices and bury them in the deposit as well? I don't know the answers to these questions, but it may be worth investigating. Okay, and then just quickly, there was a recent press release from the NIWA crews that went out to study Hunga Hapai after the January 15th eruption. If you haven't seen the Goes West and Himawari images of this eruption, that is one of them, and it reached the mesosphere, the central overshooting plume. That's 58 kilometers height. That is astounding. And I did quick measurements of it when those images came out, and I didn't believe it, neither did Mark. And then NASA did a study and confirmed it, and I was like, okay, that's crazy. So that was astonishing, and this eruption is astonishing for many reasons, but I'd recommend going to their website and looking at this press release. They're starting to release tidbits of their results from this cruise. And what they did was they went to the scene of the eruption, and they've been mapping the seafloor around it. And they found that there was very extensive pyroclastic density currents that were flowing along the seafloor during this eruption, or underwater landslides from collapse of parts of the caldera. But their interpretation is that these were primarily pyroclastic density currents. They flowed over 80 kilometers away from the caldera. That's incredibly far. And they severed some of the seafloor communications cables with Tonga. There also is evidence from multiple pulses of these flows along the floor. Okay, sedimentation waves. Yeah, maybe not. You could have variations in the eruption source parameters that could have caused multiple pulses of collapses as well. But perhaps sedimentation waves should be part of the consideration. So I'm excited to see more data come out as they publish the papers from these. Okay, that's enough of me talking. Thank you.
Questions for Yoshi? And Roland, do you mind monitoring online?
Yes.
Well,
I really liked your model, these terrace deposits. Would there be a prediction for the sort of grain distribution that you would observe in sort of each sort of length of the deposit?
Yeah, so we, Colin, Raul, Mark, and I had a discussion about this briefly one time, and our initial thoughts were that perhaps you would see some change in the particle size distribution of each of these terraces with distance. An initial simple thought is that you would have coarse particles preferentially settling out early on, and then so basically a fining of particle, like a smaller diameter, smaller medium diameter as you move out through these terraces. Michael brought up the point that if you were to core these, you might see a vertical change in sorting as well, which apparently is really prominent in turbidites. So that's another idea if you go out and sample these. But I think those are great questions, right? Because there are cruises that are going to go out and potentially sample these. And those are the kinds of questions we should ask to really distinguish, is this really happening in nature, or could it just be landslides that are producing these terraces that we see in nature?
And then just to follow up from that, I don't know if you could sort of, these things would be preserved in the geologic record. That could be a thing to look for.
Yes, I think in some of the seismic imaging, if they're buried, if that's what you mean, you could see them, buried in the subsurface. Perhaps there's a tephra fall or some kind of depositional event that just blankets the seafloor and buries their expression. And so the only way to see them would be to seismically image or subsurface imaging.
I was going to follow up on that with the seismic imaging. You had one example earlier on, and could you see kind of these horizons? And, perhaps do these horizons give an indication of maybe, the frequency of these sediment waves? Or, I don't know, something, does it provide any information?
Yeah.
It's a lot like cross-bedding also.
I think Harriet's talking about the Pope figure.
Yeah.
I don't know. Perhaps it was very brief. Yeah, if you could make out horizons, is that?
Yeah, so you
maybe not.
You can, I think, maybe start to see horizons here. And I think Martin Jutzler has interpreted some of these to actually be rotated blocks, and that lends credence to the landslide or slumping theory.
Okay.
I'm not convinced just from this image, but I don't have access to the raw data. So
what kind of scale would that be, like the thickness of the?
So this scale bar here is 160 meters. So some of these are order 150 to 200 meters tall. And then that wave height, you could call it, decreases the distance or crest height. An interesting thing here is that Martin and Ed Pope, they interpreted this as ponding in this dip that's right near the caldera rim here. If you interpreted that as this deposit is being in place by sedimentation waves, that could be evidence for scouring.
Yeah, right.
Last question. I mean, in the example that you did with water, when the plume comes back down, it's naturally going to be denser than the water because it starts as water and it's got sediments in it. Is there a situation in nature where the thing that comes down could actually be entirely less dense than water and it wouldn't go to the bottom at all? Sort of like your pumice cloud thing, except saying that everything does that. Because with your experiments, it was inevitable that it had to go down, right?
Yeah.
But I'm just wondering, in nature, is there an intermediate where the thing could come back down?
Yes.
And it would be less dense than water and it wouldn't go into the water?
I think so. And so we did do some experiments I didn't show where the fountain breached and it had, I did a dense saltwater layer rather than a freshwater layer in the tank, and then injected freshwater mixed with particles. So the freshwater in the mixture was buoyant relative. The particles weren't.
Made it dense.
So when it impacted back down, most of the mixture did indeed go down and the particles dragged the buoyant fluid down, but we did notice some surges of the buoyant fluid extending out, which suggested that maybe you're getting phase separation and the buoyant fluid being accelerated outward. And maybe that spreading as they hit the water surface is giving them enough of a kick that you can induce particle fluid separation. That actually was the goal of that experiment, was to just explore that idea.
And so you would then expect to see the sediments, these layers in that context, because you're still putting the sediments in the bottom, right?
Yes. Did we see it in that? I believe so. You know what? I don't want to tell you the wrong thing. I have to go look at the images again. One cool thing, if we have time, we did try to simulate a pumice raft. And it's just a really cool video, and I want you guys to see it. So what we did is we put a bunch of buoyant plastic particles floating across the whole surface of the water, and then we injected one of our coarse sand water jets into the tank, had it breach. And what you'll notice, it's hard to see, but some of the buoyant particles do get dragged down by the sedimentation waves all the way down to the deposit and carried in the gravity currents flowing along the tank ground, and then they float back up. Now, Michael has pointed out, and I admit this too, we just did this. I did not do any scaling analysis to say whether or not these plastic particles actually scale to, say, giant pumice correctly. But it was just to explore this idea, what would happen if you had a pumice raft there. Something we could maybe explore in the future, I don't know. I think, are there questions online?
Kristen had a comment. Kristen, do you want to unmute if you can, or I can read it for you?
Sure. I was just briefly going to say that we saw pumice raft formation following eruption last year, the 2021 Fukutoku Okinawa eruption, where we think there was partial column collapse that then formed mostly a floating pumice raft on the surface.
Okay. So like what Bruce was talking about with the collapsing, yeah. No, I don't see why. Yeah, I don't, that could easily happen. I can totally see that. Yeah.
Other questions or comments? It's interesting for that Tonga eruption that it took a while to realize that the vast majority of the mass never went up into the atmosphere. And that was one of the best documented eruptions ever, at least with satellite measurements.
Yes, I was watching it and I was like, we can't really see what's going on in the interior. I bet there's a lot that's going into the water. I think I tried looking at some of the tide gauge measurements, pressure sensor measurements in various parts of the Pacific Basin to see if you got the signal of that huge initial tsunami, but would you get a signal of multiple tsunamis occurring throughout? Now, there were explosions, right? So I can't just say that's from more collapsing material, but my hunch is that there is always a lot of partial collapse going on with these kinds of eruptions. We're so fascinated by the visual image of that going so high in the atmosphere. It draws our attention, and the reviewers of my paper on this, I think, are affected by that a bit. But that, I got the reviews from them. They're questioning, how much goes under. And then the NEWA thing came out. The day I got the reviews, I was like, so now I've got some.
My understanding is the best estimate is 6 to 7 cubic kilometers by volume of the submarine, and about 1 cubic kilometer of subaerial.
Wow.
And Kristen's on the line. She estimated the volume that erupted.
Oh wow, that was just telling me I was waiting for those numbers.
That's none of it's published.
Actually, have to forget that.
We just recorded it.
Should I end the recording?
So let's thank Yoshi again.
Thank you. Those were great questions. Actually, some of the best questions I've had.